Hash functions are functions that calculate short hash values for binary data such as strings, documents, or executables. If the hash values calculated are such that the hash values can be seen as uniquely identifying binary data, then the hash function can be used to verify the integrity of binary data by comparing the hash values of the data instead of comparing the data itself. Now, no hash function can uniquely map binary data to hash values, as the set of hash values is much smaller than the set of binary data, but if it's difficult to find collisions, meaning that the hash function is collision resistant, then the hash function is deemed fit for cryptographic integrity purposes. The four most common hash functions implemented are message digest 5, MD5, and the secure hash algorithm family SHA-1, SHA-2, and SHA-3. And in the following demonstration, you will see how I made use of these four hash functions in Python to calculate hash values, and how I explored that message digest 5 and SHA-1 are not collision resistant and as such are not secure hash functions fit for cryptographic integrity purposes, as for each of these hash functions differing binary data exists that are nevertheless mapped to the same hash values. Using the four hash functions MD5, SHA-1, SHA-2, and SHA-3 with the cryptography library in Python is straightforward. All these hash functions live within the hashes primitives module of the cryptography library, and creating a hash object requires it to pass the desired hash algorithm. If the binary data is just the input string presented on the slide, reading fundamentals of cryptographic hash functions and creating an MD5 hash object, it's clear that the hash value created for this input string is the same 128-bit hash value as presented on the slides. The three lines for calculating hash values I extracted into a simple function in order to ease the next parts of the demonstrations where many more hash values will be calculated. With this helper function, it was then easy to explore SHA-1, SHA-256, and SHA-3 512, and to verify that each of these hash functions indeed calculates the hash value as presented on the slide, which is due to all of these hash functions being deterministic functions. Now that the use of hash functions in Python was clear, it was interesting to verify that MD5 and SHA-1 are indeed not secure cryptographic hash functions for integrity purposes. For MD5, I created two PNG images that are very clearly different images, with the first one having an all green background and with the second one having an all red background. These images I then modified with a script I found on the Corekami Collisions GitHub repository, so all credit for the following demonstration goes to the Corekami Collisions GitHub repository. The modification of my two original images with the Corekami script took fractions of seconds on my very average desktop machine, which underlines how easy attacking MD5 nowadays really is. In order to verify the insecurity of MD5, I read each modified PNG image into memory and calculated the corresponding MD5 hash value. The insecurity of MD5 is then demonstrated by demonstrating that the PNG images are indeed different images, which is visually already very clear anyway, given the green and red backgrounds of the images, but that these two clearly very different images have the same MD5 hash value. What is now really demonstrated is that MD5 is not a tool fit for the purpose of verifying the integrity of data, as the data can be easily modified without MD5 being able to detect the modification. For the following demonstration of the insecurity of SHA-1, all courtesy goes to Google's shattered.io, where two PDFs can be found, which again are very clearly very different PDFs, with the first PDF having text on a blue background and the other second PDF having text on a red background. Verifying the insecurity of SHA-1 then proceeds along the same lines as with MD5 by first reading the PDFs into memory and then calculating the SHA-1 hash values for each of the PDFs. The insecurity of SHA-1 is then demonstrated by verifying that the two PDFs are indeed different PDFs, but that the two PDFs have the same SHA-1 hash value. The last part of the demonstration was then to verify that SHA-2 with 256-bit hash values doesn't collide on both the MD5 image collision pair and neither doesn't collide on the shattered.io SHA-1 PDF collision pair. Along the very same lines, this could also be verified for SHA-2 with 384 or 512-bit hash values, as well as for all of the SHA-3 hash family. This concluded the demonstration of the use of cryptographic hash functions in Python and the demonstration of MD5 and SHA-1 not being secure hash functions fit for the purpose of verifying the integrity of data.